Today we have talking with us Taylor Hoffman-Ballard with Evergreen Stormwater H2O. She's familiar in the Eastern Washington. She does a lot of work with us and for us permittees. Taylor comes to us from Wisconsin?
No, Minnesota.
It was a test. She comes to us from Minnesota. In her spare time, she likes to play hockey. She does research, science research in her home for her career. It's kind of inspiring. And she's giving a co-talk today with Drew, who's a municipal employee with the city of West Richland. And they're doing a study, and I'm going to leave it there and let them tell us what they're going to do. They are looking for ways to involve water and wine in conservation, but I'm not sure where you guys were going with that. This is a water conservation. I'll leave it there. Take it away.
All right, can everybody hear me in the back? Great. Okay, I'll do my best to project my voice. Today, we're going to be talking about the performance of a non-vegetated filtration swale BMP that we tested in West Richland this last summer and fall. First, we'll go through and we'll give a background of the study. We'll go over the study design. We'll give a review of the data collection. We'll review the data analysis. And then lastly, we'll give a summary of findings and recommendations. That'll highlight the design and maintenance guidance we came up for the study, and then items that we identified for future research. And then it's your turn.
So the non-vegetative swale is basically, we use the guideline, the structure of a biofiltration swale, but instead of having vegetation, we used rock layers of different types of rocks and tested those. It's very attractive to an area like Tri-Cities. We get 7 inches of rain a year. So if we have vegetation, anything, we've got to be putting water to it. We got to be extra maintenance to it. You know, in the West Richland, 40% of our water we produce annually goes to irrigation. It's put on the ground, which is about 450 million gallons of water. So anytime we have the ability to not irrigate is an attractive option for us. So we did get gross grant funding for this in 2021. We applied for it, and it fills the effectiveness study requirements for City of Richland, City of Pasco, City of Kennewick, City of Walla Walla, Walla Walla County, and then the City of West Richland. As part of the study, we produced the QAP, final report, fact sheet, and then when everything's wrapped up, City of West Richland will have it on our website, and I'm sure all the other participating entities will have it up on their website too for anyone to view. So the City of West Richland, we were the lead entity for the project, and then the participating entities, Richland, Kennewick, Pasco, Walla Walla, Walla Walla County, and City of Pullman, Moses Lake, Idaho Department of Environmental Quality, and Washington State Department of Ecology were the technical advisory committees. And then consultant, we hired Evergreen Stormwater to be our consultant on this. Kudos to their group and Taylor. They really are what drove this project to get done. We needed somebody to come in there that could really push this through and keep us in the right direction. And then also get some kudos to the maintenance guys that worked on this at City of West Richland. They were kind of told they had to do this. They have full-time jobs, and some of them spent a lot of time building and then swapping the swells out and then helping us with monitoring. So they were a big part of this. So this is our municipal services building in West Richland. We were fortunate enough to have a 430-foot swell already in the back of our facility. So we were able to use that footprint, regrade it to the grade we need in the section that we needed for the swells. And we were able to break that 430 feet into 2 swells. So when we did this study, we were able to test 2 different studies or 2 swells at a time. And then we took that media out, tested 2 more swells, took that media out, and then picked the best of the performing ones. They'd find a final test out of that. So we were trying to make sure we used rock that could be available to all regions instead of just something specialized out of a landscape company in the Tri-Cities. So we really tried to spend a lot of time finding materials that anybody should be able to get their hands on, so that we didn't spec something that works for us and no one else. So alternative 1, we used 7.5 inches of HMA gravel, basically the 1/2-inch chip for HMA. Alternative 2, we used 7.5 inches of pea gravel. But with that rock, since it's small, the influent would move the material around. So we had to use a 2 to 3 inch ballast at the influent location. And then alternative 3 was 7.5 inches of gravel backfill for dry wells. And then the final alternative we tested was 4.5 inches of sand with 3 inches of pea gravel on top of that. And then we also had to use ballast at the influent. This popped up, I didn't realize I did that. Sorry. And then this kind of shows the setup we had. This is after we had installed the first 2 swales. We had a 1,000-gallon tank here that we filled with water and added silica sand to simulate the TSS loading. We had a generator with a pump inside of that would agitate the TSS so it wouldn't settle out. It would stay mixed the entire time. Another generator and a pump that would then pump it out through the PVC system. We had an isolation control valve here so that when we tested the flow, we could make sure we kept the flow at the flow rate we needed for each test. And as the water dropped, we could adjust that to make sure we stayed inside the numbers we needed. And then it was piped over here where we had an inline meter, so we could digital meter, so we could see how much flow was going through it. And then our little homemade distribution barrel here that dumped into the swell. And then the first 4 swells we had an impervious liner, so all this was a PVC liner. We actually had some spare liner from our treatment plant, so we came in here and cut that. So this was all on an impervious liner.
All right. Yep. All right. So using that influent distribution system, we simulated storm events. We were simulating 6 water quality design flow events for each swale alternative that we looked at. After each of those water quality events, we then would run an annual, like the equivalent annual TSS load through the swale to simulate a year having passed and to see how treatment performance would change over simulated time. We only did this 5 times because that last swale was just meant to get water quality samples. So the sampling that we performed, actually I'm going to show real quick. This is what the annual TSS loading looked like. We sent 14 pounds of TSS, which was silcosil, down at the influent, so at the very start of the swale. When we conducted sampling, we were collecting 3 grab samples at the influent, and those were spread out across the simulated storm event. And then we were also collecting 8 effluent samples at each effluent sample port, and those are spaced 25 feet apart in the swale. We're collecting those samples in the rock, so it's the water flowing through the rock that we expect to give us treatment for TSS. Those samples were also grab samples that we collected right as water arrived at those sample ports. So those samples reflect a first flush of the system. So we anticipate they'd be a little bit higher than like an EMC or event mean concentration would be. So now I'll go over a review of the data collection. I'm just going to quickly summarize the 4 swale alternatives that we looked at. They're summarized in this table by rock type. I'll start off with HMA gravel. This did 3rd best overall. One of the advantages of this rock is it's really readily available. However, it can be challenging to find washed or clean because of its application. The pea gravel is the next rock that we have in this table. This actually did the best overall in terms of treatment, but it was very inconsistent. So we would have some high removal by the end of the swale, but then we would also have some leaching by the end of the swale. One of the advantages of this type of rock is it is typically used to choke out sediment, but there are a number of disadvantages, including it can be potentially more expensive. It does require a larger rock to stabilize the swale if you use this rock. If you step in it, it kind of smushes out. And then when we'd send high flows through it, it would kind of erode out and it would get blown around by blowers when we were trying to do maintenance tests. It's also likely very sensitive to fines. This had the highest background concentration of any of the rock that we got from a supplier. So it's likely that it would need extra care during construction or transport. And then this rock also provided too much resistance for the water to flow fully through the media. So we wanted all of the water quality design flow to travel through 7.5 inches of rock to provide treatment. Because this provided too much resistance, there was water traveling above and we weren't getting that full treatment. The next rock type we looked at was gravel backfill for dry wells. This did 2nd best overall. It's another readily available rock. It doesn't need the larger rock to stabilize. It's already fairly large. It doesn't move around very much. One of the drawbacks was during the initial testing, we weren't sure if it was going to provide sufficient treatment. It did fairly well for the first 2 events and then kind of dropped off. And then the last rock type or combination that we looked at was 4.5 inches of sand under 3 inches of pea gravel. We used the same sand in the sand filter BMP, so we had thought that would provide some treatment, but we had similar drawbacks to the pea gravel where we saw too much resistance through the media. We also anticipated that the sand, because it looked fairly fine, would migrate through the soil over time and move. And then this alternative would also require a larger rock to stabilize over the top. So from that information, we came up with our final swale design. This was the 5th swale we tested. We did not use a liner for this option. We allowed for infiltration, and we did that by putting a 3-inch layer of pea gravel at the bottom of the swale and then 7.5 inches of gravel backfill for drywall. That 3 inches of pea gravel was meant to provide for infiltration while keeping the existing ground from migrating up into the gravel backfill for drywalls. We did change up how we did water quality events and sampling during the final test. Instead of doing 1 water quality event followed by an annual load, we did 2 water quality events, an annual loading, another 2 water quality events, an annual loading, and then 2 water quality events. This was meant to simulate 3 years, which was based on the initial testing of the gravel backfill for dry wells. That's where it looked like it would potentially need maintenance to restore treatment performance. We did end up having to make a couple adjustments during testing. When we had the liner, when we removed the liner for the final swale, we ended up seeing erosion at the downstream end. Even though we had kept a section of liner and tucked it in, water was able to get around that, created erosion right at the end where our last sample port was. So in order to keep that sample port and be able to collect samples there, we ended up installing a small weir right after event 3 that was just at the height of the pea gravel. That weir ended up getting eroded around again. So then we installed the large weir that you see in this photo with the wing walls to force water in towards the sampler. So these were 2 adjustments during testing that ended up slightly changing our results that I'll talk about later. One thing I do want to mention is we were very careful to not disturb the rock or put dirt into the rock. And even after we put the weir in, we rinsed the rock thoroughly at this location to try and reduce any impacts. So now I'll go through a review of the data analysis for just the final swale. This table, and I'm going to step through it, shows the original water quality concentrations for TSS for the final swale. On the left-hand side, we have the location swale, the influent at the top, and then every row is one of the sample ports, so at every 25 feet, ending with the 200-foot swale length. I want to mention again, we applied that annual TSS load, so 14 pounds of TSS at the influent of the swale after event number 2 and event number 4. So that's why you see those fairly high increases in concentration at the upstream end of the swale. That also means that the first 2 events would simulate first year, the next 2 events would simulate the second year, and then the last 2 events would simulate the 3rd year. As you can see from our percent removal from influent, this is the percent removal from the influent to 200 feet. We get fairly good removal for the first 2 events, and then we see a significant reduction in that percent removal for event number 3 and also event number 5, with some recovery for event 4 and 6. These 2 events happened right after we installed that weir. So even though we rinsed that rock, we were careful with it, you still see a 20 to 30 milligram per liter increase from, let's see if I can do this, 175 to 200 at those 2 events, which makes us think that's fairly large compared to the rest of the variation in those concentrations, which makes us think that that weir was what caused that increase at the very end of the swale. So what we decided next was we wanted to understand how the swale would have performed without the impacts of those weirs. So we used a trend line analysis to understand the performance of that swale at 200 feet at that last sample location, and to determine whether the swale would have met tape treatment performance goals at 80% TSS removal. When we ran this trend line analysis, we took out the data at that very last sample port for events 3 through 6, even though we did see some recovery for events, I believe it was 4 and 6, those last sample ports still saw a slightly higher concentration, so we took those out to remove the impact of the wear. So from that trend line analysis, the best fit appeared to be linear trend lines for events 1 and 2, 3 and 4, and 5 and 6. So these are for one trend line for year 1, 2, and 3. This makes sense because we would expect as we were loading the swale with TSS that the treatment performance would change. On this slide, we have the trend line for year 2, and you can see that we're meeting, this blue line is the trend line, and we're hitting that targeted TSS % removal before the 200-foot or end of the swale. For the next graph over on the right, for year 3, we're just barely missing that targeted TSS % removal by the end of the swale, which makes us think that for the first 2 years, we would meet that targeted 80% removal, but between year 2 and 3, we would need to perform maintenance to restore treatment. So I'll go over a quick summary of findings and recommendations from the study. Like I just mentioned, based on the trendline data, we found that the swale meets treatment performance for that 200-foot swale length, and that maintenance cycle would likely fall between 2 to 3 years. We are recommending that this BMP be considered for CULD approval because of the promising data that we had based on the trend line, and then also in order to collect some additional information that I'll talk about in a slide or two. We did develop design guidance for this initial BMP. 2 things we want to highlight are the residence time, which is 50 minutes. So that would be the minimum amount of time that water would need to travel through to get the treatment performance that we experience in the field. And then the next item is, thank you. We recommend that the supplier washes rocks shortly before pickup. Did you want to talk a little bit about this?
Sure. One of our biggest struggles was what a rock supplier considers clean is not necessarily what we consider clean. Our guys had a heck of a time washing, I don't know how many, probably 100,000 gallons plus of water we used trying to rinse all this rock out. And it was a major struggle. And it was, I think it impacts some of the results because of the fact we just could not get the background sands and fines off of the rocks.
Yes. So for that final alternative, what we ended up doing was going to the plant directly and talking to them. And they had actually indicated they could wash the rock shortly before pickup and get it down to what the spec indicated. Whereas if you let it sit in the yard for a certain amount of time, that background amount of, I guess, what we consider TSS goes up in the rock. So part of the design guidance is recommending that the supplier washes the rock shortly before pickup. That translates to an extra cost per ton of about $5 to $20. It's less if you have more rock, is how we understood it. The other major thing to consider is just protecting the rock during construction from dust, from stormwater runoff, so that you don't introduce those fines before the BMP is online. And then lastly, some future action recommendations that we identified during the study. The first one is determining maintenance actions to restore treatment. While we did tests for what the maintenance cycle would be, like when you need to perform maintenance, we didn't look at what actions would actually restore that treatment. That would require additional testing. We would also want to observe any future installations, especially long-term installations, for frequency of minor maintenance actions like cleaning out an inlet or weed growth. Since each of our swales were only installed for 1 to 2 weeks, a lot of them had liners underneath. We didn't see any weed growth. So it'd be something to look at. And then lastly, we'd want to assess the impact of a catch basin at the inlet, flow weighted samples, and real storm events on the swale. The catch basin at the inlet we anticipate could affect the treatment performance and extend potentially the maintenance cycle. The flow weighted samples, because I mentioned earlier that we took grab samples at the very start of when water came through the swale, those flow weighted samples might show a slightly different % removal than what we experienced, potentially lower, or an improved % removal. And then the real storm events, since we're sending 1,000 gallons down the swale at the peak water quality design flow rate, those real storm events could potentially impact treatment too.